I am blue.
You out there? There she is. Um, I want to, so I have looked ahead to the next section. We're about to get into a probability section. So I do want to do what I said we were going to do. I want to focus some more on fractions because fractions are going to rule our life. Probability is all about ratios. Um, so let's talk about fractions a little bit more. I know we've already talked about them before a bit. You can always use some more practice. And then I want to go into what we already know about probability. In fact, let me try to do something fun. Let's see if I enjoy this. I don't know. This is new for me. I'm a math teacher. We're not used to being fun. Let's see if you guys agree with me. My idea of fun might be very different. I don't think I did this yet with you guys. Did I ask you about like, I'm pretty sure I didn't do it. I'm going to participate. So get out a nice blank sheet of paper. Don't worry, not a quiz. It's not a quiz. Let me see if I can wait for more people to come. This works better with more people. So let's do this. For right now, write down on the piece of paper. I was born September 21st. Anybody else born September 21st? Wouldn't that have been neat? All right. So I'm going to put a big ass 21. Do you see that? I put a big ass 21. You with me? You with me? So if you were born March 11th, you put a big ass 11. If you were born January 2nd, you put a big ass 2. So do it. Just do that right now. And then I'm going to use that in a bit. I'm going to wait for more people to show up because it works better when there's more people. And obviously this is going to work better. If you don't have a camera, I'm just going to ask you to respond in chat at the appropriate time. There we go. I got one more person. So let's do this. I'm going to come back to that in a minute. Just hold on to that. All right. I like it. Let's focus on fractions for a bit. So very special. Let me see. Let me do this. Let me spotlight myself. On spotlight. There we go. Okay. So some real basics about fractions. We've already talked about stuff like how to reduce fractions and so forth, but there was a problem on the quiz that got me a little concerned. So if I had 43 Democrats, 31 Republicans, and let's say 10 other, right? 43 Democrats, 31 Republicans, and 10 other. I like it. Can somebody help me figure out how would you do the percentage of the people in this group that are Republicans?
Start by finding the total amount for the whole thing.
I like it. So it's going to be out of what's the total amount?
84.
84. So out of 84 people, and what's weird is, not what's weird to be honest, the math is exactly the way that we say it. Out of 84 people, out of 84. That's what out of 84 looks like in mathish, isn't it? Out of 84. How many were Republican? 31. And then whatever the hell that is. It's like 35% maybe. I have no idea. Maybe a little higher. Does anyone have a, oh, I forgot. Can you guys, all right. I hate calculators. I do. I actually do. I really hate them. But they are also very important. You need to have a calculator. I feel so bad for those of you. It does not cost a lot of money to get a scientific calculator. They cost like 15 bucks. If that is a lot of money, let me know. I will get you a calculator somehow. Okay. Yeah. I suggested that if you're going to take 160 next, you should really get a TI 80 something or other calculator, and you can rent one of those for $9 a month. But you want to get kind of used to that one. But for right now, you just need some calculator. Because some of you guys, I don't know if some of you guys are doing so much work because you think I want to see every little thing. I do not. So if this was the problem here, I don't need to see you do long division on this. I don't. We did the work already. That's the work. Now to get the answer, I can throw in a calculator. Right? So somebody help me out. What is 31 divided by 84 as a decimal?
0.3690.
All right. I like it. Does that match up? Anybody else get the same thing? All right. So then I would write that. How would I write that as a percentage to one decimal place?
36.9.
And just to remind you, I have to show off sometimes. My suggestion was 35 or 36%. I think it's, and some of you guys like, it's not good enough, math boy. Come on, step it up. I'm sorry. Okay. Right. So is that all right? So we had a lot of trouble with that first problem about the M&Ms, but it's exactly the same as this. And the thing is, I told you the total. You didn't have to take a minute to calculate the total like we did here. So it was so many out of 48 for that first problem. So there were 10 brown out of 48, 10 divided by 48, and then you can make it into a percentage. And what's supposed to happen if I keep going? Is everybody cool with the way I'm writing this? Percentage Republican, right? Just a little quick way to do it. Percentage of Democrats would be what?
(43/84).
Yeah. And that's just over 50%. I'm going to say 0.506. I don't know. It's probably less than that, 0.50. I don't know. 0.503. Nobody's going to help me.
5119.
Shoot, it's higher. 5119, blah, blah, blah. So then what would that be as a percentage to one decimal place?
51.2.
Kick ass. And of course, if I did this one, all the percentages have to add up to be what? If I add up all the percentages, if I figure out probability of other.
100%.
Yeah. So just like on the M&M problem, you just, whatever you did, add them all up, add up all the probabilities, the percentages, they have to add up to be 100%. If not, or close to it, right? Because there might be some rounding. If they don't, that means you made a mistake. Okay. Now, I kind of threw a word in there that is another way to look at a percentage. It's the probability. So if you think about it, if there were 36.9% of a group of people were Republicans, what's the probability that I pick a Republican at random out of that group? 36.9% chance. And most of the time, most of us kind of understand that level of probability. That's the basic idea of probability. It's related to the percentage of something. It's the chances that something could happen. Okay, maybe. Okay, so that's one big thing because we're about to get into probability, and probabilities are all about ratios, amounts out of totals. All right. Let me show you, let me do this. I like this kind of problem I'm about to show you. I think somebody just came in, so I don't know if anybody's still copying this down. Is everybody all right out there? Oh, have I started recording? Yes. All right, I'm going to assume yes because nobody's saying no. Here we go. So this kind of problem kicks so much ass because it kind of puts together a few things we've done. Interesting, Jeff. Oh, that's right. So let's say, well, let's see, how do I want to break people up? Let's do, yeah, sure. Teacher, student. Yes, no, maybe. So I ask a group of teachers and students a question. You guys kind of with me so far? I mean, nothing's happened yet, so yes, you are. So I ask a group of teachers and students a question, and they can say yes, no, maybe so. So let's say that 51 teachers say yes, 7 say no, and 2 say maybe. 13 students say yes, 89 say no, and 7 say maybe. I'm actually going to leave it up to you to come up with an idea of what the question might have been. I don't know. I don't have anything in mind. All right. So if I ask you what percentage of everybody, what percentage of the group said yes, what do you have to figure out first? I want to know just the percentage of everybody I spoke to that said yes. Oh, I need to add something on here. Add this other thing on here. I might as well be completely open. See that? Add another row on there. You'll see why in a minute. What do I have to do before I can figure out the percentage, the probability that I get somebody who said yes? What do I need to figure out first?
The total number.
Total numbers of everything, right? So how many people said yes?
$64.
Cool. And then no would be 96, and then maybe would be 9. How many teachers did I talk to? Looks to be 60. Is that right? And how many students did I talk to? It looks to be 109. Let me stop just for a minute. This is something called a contingency table. Does it matter what it's called? No. And you've seen tables like this before. So how many total people did I talk to?
169.
Yeah, 169. I love it. So if you do it this way, 169, and if you add these up, it better still come out to be 169. Does it? Yes, thank God. All right. Is anybody not with me so far? Is everybody relatively okay out there? Just a slight earthquake, sorry. Okay. So then what is the percentage that said yes? How many said yes?
64.
64 people said yes. Is we cool with that? Out of
169.
169, I love it. And then you just gotta do that. So go ahead and finish that one out and then do these two also. I don't know if you can read that. Whoa, I can get really high off of that one. Jeez. Whew. Calculator. So I get this. So I get 37.9% for yes. What do you guys get for the fraction for student? How many students are there?
9 over.
109.
Yeah. And then, of course, yeah, out of 169, and the last one, I don't know if anybody got the last one. The last one's a little bit freakadelic. You might actually not even be able to read it. So the probability, I picked somebody who's a teacher and they said maybe. So that person that I pick has to do both. How many people could it have been then? How many people match what I'm looking for here? They have to be a teacher and they said maybe.
2.
Yeah, there's only 2 who are teachers and they said maybe. There's only 2 of them. Do you guys see that? I've only got 2 chances to get what I'm looking for. That'd be a teacher who also said maybe. Only 2 out of 169. And that's going to be a very small percentage.
1.18%.
Yeah, points. Yeah, I see which 0.118. So that'll be 1.2%. Once, twice, and then that goes to a 2. Is that? Do you guys see that? Let me know if you don't see that or get that. Okay, I like it. Hey, Mikey. So again, this is just another way to give you data. So here's some data from a group that I talked to, and then we can calculate various things. All right, what if let me push this a little bit. I was in my head thinking, do I want to try this or not? If I ask you, let me see if you guys get this. What percentage of the teachers? What percentage of the teachers said yes? So what changes now? What was the same for all of these problems? What was the same for all of these problems?
The total was 169.
Yeah, because I was talking about anybody. It could have been anybody. Now it must be a
Teacher.
teacher. So now what's the bottom going to be?
60.
60. It can only be out of those 60 people because it must be a teacher. So out of 60 teachers, how many said yes?
51.
51. Can't say this because that includes students. Can't be a student. So 51 out of 60.
85%.
Yeah, 85%. Like I was almost there. Now what? Real quick. Is everybody with that? You guys see that? So the denominator relates to the total amount that it could have been. So these are all 169. It could have been anybody. I didn't say that they were any kind of person. Here I said, what percentage of teachers? Okay, it's got to be teachers, so it's got to be out of 60. The percentage out of everybody said yes was only 37.9, but 85% of teachers said yes. So obviously, whatever the question is, teachers agree with it very much and students disagree very much, right? So you can imagine possibly a few different questions that could be. All right, maybe. That's a lot of good shit. There's some good data. There's some good math happening. All right. So Now I want to transition into the book and look at some examples of what you're going to actually have to work with. Push this guy away. Go away. Good boy. Okay. Oh, let me come back to this. I got a few more people that joined now. So, well, one more person. So whoever joined after I said to do this, I was born September 21st. So I have written 21 very large on a piece of paper. So if somebody has not done that yet, so if you were born April 28th, you will write 2-8 on a piece of paper. If you were born February 29th, that is really interesting. And then you write a 2-9 down there. Okay, so go with me on this. How likely is it that two people in here have the same birthday? I love it. We don't really have a good feeling. We feel like it's very low. 28 of us, it's still, once you get to 34, it's more likely that at least two people have the same birthday. So this might end up being disappointing for me. But normally on the first day of class, when I do this in my statistics class, and I have like 50 people in there, I've had 5 sets of people with the same birthday. And I don't count twins. You with me? Because that would sort of be cheating a little bit. If I ever have twins or triplets in a class, I just don't count them. Not that they're bad people, but it's obviously sort of cheating. But let's just see. Let's just see what happens. This could very well lead to nothing. Where are my January babies? My January babies. If you don't have a camera and you were born in January, can you chat your day of birth? Anthony, you okay? What's up? Oh, are you just raising your hand that you're January? So what I need you to do is there you go. See how Melissa did that? All my January babies, either hold up your number or put it in chat. Any other January babies? There we go. Stuff's happening. Is that all my January babies? All my January babies? All right. So what about February? February babies. Put your number up or put it into chat. Oh, let me see now. 4. Cameron, is that 20 or 10? All right. I like it. And there's 15. Okay. No birthday twins yet. What about January, March? Oh, wait. Giovanna, is that for March? Or is that for February?
For February.
February. Okay, thank you. So no matches in February. March, I got Caleb is in March. Lauren's in March 2nd. Oh, look at that. Ryan. Oh, wait a minute. Lauren, you're born when? March 2nd. And Angelica was born March 2nd. That's awesome. I'm sorry. I'm very excited. I'll keep going. We'll see if we get some more. See, so it seems very counterintuitive to the human brain to think, I mean, how many days are there in a year? 365, 366, depending on leap years. So we think there's no way. What the shit? Nobody's got my birthday. That's where our brain goes. And when I say at least two people have the same birthday, how many pairs of people are in this room right now? Room. On my picture, it's Ruben is up there next to me in the corner. So Ruben and me, Ruben and Angelica, Ruben and Aubrey, Ruben and Cameron. See, already I got a ton, and I haven't even matched me up with everybody yet. And then I haven't matched Angelica up with her. There's so many more pairs of people in this class than we realize because our brain is not hardwired to do this stuff. The only probabilities our brain is hardwired to do is stuff like, if I go that way, they're at this time of day when the sun is there, saber-toothed tigers are over there eating. So I probably shouldn't go that way because I have a higher chance of dying. So the probabilities that related to us surviving are certainly built in because that's what led to us evolving and shit. But like the weirder probabilities, like the birthday thing, that is not hardwired. That is completely counterintuitive. All right. January, February, March, April. Where are my April babies? April babies. So I got the 5th. Is that it? April 5th. It's all you, Ruben. That's your month. April, January, February, March, April, May. Where are my May babies? Any May babies? Maybes? My maybes. Well, there's another April 12th. All right, see, May 18th, May 25th. Okay, no more twins yet. January, February, March, April, May, June. Where are my June babies? June babies. No June babies. All right. What was 9 months before June? Well, must not have been that cold or anything. January, March, April, May, June. July. Oh, there's June. Fantasia, June 25th. That's all you. Linnell's July. July what, Linnell?
July 14th.
Oh, so close to Lauren. July 16th. I love it. August. August babies? No August babies? There's an August baby. What is it? 29th. August 20th from Vu. Carrie, August 29th is my little brother's birthday. That's neat. But he's not in this class, thank God. I love my little brother, but sorry, Jim, if you're watching this. I know you're not watching this. August, September. That would be me. I'm up. Yay! September. Is that my? Normally, there's a lot of September babies because it was cold 9 months before. Let me see. September, October. October. Andrew, jumping the gun. I love the November. Oh, there's Ian with September. Okay, thank you, Ian. What about October? Any October babies? And all right, no, Andrew's a November baby. Any other November babies? No more November babies. And then what about December babies? Any December babies? 27th for Tanya. Oh, there we go. We got another. Oh my God. Daisy and Tanya, both born December 27th. So we got 2 birthday twins out of such a small group of people. That just makes me so excited. So what's my point there? It's that probability is difficult because it's not something hardwired in our brain. It just isn't. So that's why we have to trust the math that goes into it. We're nowhere near the point where I could show you the math behind the birthday problem, but you can certainly look it up if you want to. The birthday problem, or how else is it called? I don't think it's called a birthday paradox. It's the birthday problem, I think, should get you there. There's another one. I'm going to put you through another one. This has got very slight interaction, okay? Just stay with me. Okay, now this is kind of neat too. Anybody ever heard the show The Price is Right? No, Jeff. Let's Make a Deal. That's the one. I don't know. They're all the same freaking game shows. Let's Make a Deal. Okay, you guys have heard of it. I think it's is it still on the air, or was it back before COVID or whatever? Because I think was Wayne Brady was hosting it. But I remember way. Oh, go ahead. Sorry.
It's still on.
Still on. Okay. I remember way back in the day, it was this guy called Monty Hall was the host. So just go with me. Just go with me. I don't know if any of you guys have ever heard this probability problem before, but just go with me. Okay. So at the end of the show, they would take people that have won money, they've won prizes, and they'd say, do you want to trade in what you've won for a chance at, $50,000 or just some insane, price? So they have to choose whether they want to participate. They want to give back what they've won so far in exchange for a chance to win more. And if they say yes, what they got to do, all right, Jeff, stop. It's fine. Okay. What they got to do is choose a door. So there's 3 doors. Behind 2 of the doors was a goat. And we're going to assume that they didn't come on the show to win a goat. They're not going to be excited if they get the little goat, right? And behind the 3rd door is, let's say $50,000, right? So obviously you want that door. Can somebody, first thing I see or hear, this is door 1, 2, 3. I've already got the prize behind a door in my mind. Could somebody pick a door?
2.
2, okay. Woo-hoo, woo-hoo. Who said that?
Carrie.
Gary, okay. What is the probability that Carrie has already won?
1 out of 3.
Does everybody see that? There's one prize out of 3 choices. So the probability she's won already is 1 out of 3. So what's the probability that the prize is behind some other door?
The same. 1 out of.
2 out of 3.
2 out of 3.
Oh, duh.
One choice that wins, but 2 choices out of 3 that loses, right? So there's a 2/3 chance that she picked one of the 2 doors that leads to a goat. And there's a 1 out of 3 chance that she's already won. All right, now here's where things get really evil. Okay. I, as the host, I open up door number 1 and I show her there's a goat. All right, this is going to be spider goat. You with me? This is spider goat. Spider goat does whatever her spider goat does. Okay. At least let me make him happy. He's so happy. All right. I open that door up. Is everybody with me? I open that door up and then I say, do you want to switch doors? The mistake people make is they don't stop to think, why did I open up door number 1? Right? So people think that it's now 50-50 and people are desperately wrong. Just because I opened that door, I did not change these. These are still true. There was a 2/3 chance it was behind some other door. So now I open that door, it's not there. So what's the probability it's there? 2/3. There's a 2/3 chance. I'm going to show you one other example in a second that's going to make this easier. I can see your faces like, I don't know what the shit you're talking about. It's 2 doors, 50-50 chance. You're insane, Mr. Waller. But you're wrong. Has anybody ever heard the show Mythbusters? They did this a long time ago. They actually set up the whole thing. They had a bunch of people come in. They actually did it, and what's called an empirical study. They set up the experiment. They let people choose, and they counted how many times people won. And if you switch doors, you are twice as likely to win. Twice as likely to win. So let me show you another. Let me watch. If you still don't quite get it, let me do this. You ready? So let me say we are in an enormous facility, and there's not 3 doors. There are 100 doors. Everybody with me? There's 100 freaking doors, and you pick one. Let's say you pick door number 37. That's our choice. Then what's the chances you won? What's the chances you picked the prize?
1%.
Yeah, because it's 1 out of 100, right? You with me? So that's why it's 1%. So probability that this wins is 1 out of 100. So the probability that this loses, that door loses, is 99 out of 100. Now, the part I really want you to focus on is I'm going to start opening up doors to show you goats. I'm not going to open the door with the prize or else the show is over, right? You with me? So I open up every door and show you a little spider goat. I open up every door except door number 2. I leave door number 2 closed. What's the most likely reason I left door number 2 closed?
Trick people.
But how? What's most likely behind door number 2?
The money.
The prize, right? I'm the host. I know where everything is. You only had a 1 out of 100 shot to pick the right door. So why did I leave door number 2 closed? Because 99 out of 100 times, that's where the prize is. If you switch, will you win for sure? No. But if you switch, do you increase your chances of winning drastically? Yes. If you don't quite get this, then I'm still okay with that because this is a good illustration of why probability is not hardwired into our human brains. It just isn't. hopefully this makes some sense. So when I, as the host, opened doors up, I provided more information that you didn't have before. So now you know that's much more likely. I'm going to switch. Hell yeah, I'm going to switch. Hell yeah, I'm going to switch. Okay. Maybe. I'm almost certain there's still somebody out there that has no idea, but I'm hoping. Okay. Enough of game shows. Let me see how much time I got left. What time is it? Oh, cool. I got plenty of time. So let's look at some stuff in section 1.6. Where'd you go? Let me share this. Share screen. Pop. All right, so you should be able to see a puppy dog, right? Puppy dog. So here's something about my little brother, just to tell you. I mean, again, I love my little brother, but he still to this day, he says to me, Jeff, are you teaching probability still? I'm like, yeah, of course I am. He says, man, what the shit, man? Everything's going to happen or it ain't. What's your problem? I'm like, holy crap, Jim. Don't become a doctor. I don't want you to be my doctor. I'm like, Doc, what's my chances? 50-50? Oh, no. What's the problem? It's going to snow tomorrow in San Diego. 50%. It's going to happen or it ain't. Anyway, sorry. I don't know why I'm picking on my little brother so much, but you don't know him, so who gives a shit? But a lot of people have that same perspective. And hopefully all of you see why that is desperately wrong. What really sucks about probability and especially statistics is that it can be easily misused. That does not mean that it's not good, that it's not useful, right? I'd rather know if I have a 99% chance of survival in a surgery versus a 37% chance of survival in a surgery. I would rather know so I can prepare appropriately, right? You guys kind of with me on this? I mean, that only makes sense. I'd rather know if there was a 10% chance of a fire tomorrow or an 87% chance of a fire tomorrow. I would probably act differently in both of those situations. Okay, maybe. Okay. Oh, that's funny. Let me see. Blah, 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 blah. Blah, 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 blah. Yeah. Blah, blah, blah. I don't know. All right, let's do this. So if I roll a normal die that has not been weighted, so it's a normal die, and the probability of rolling a 4, why is the probability of rolling a 4 1 out of 6? Because like they say, there's only one side with 4 dots. Okay. We're assuming nobody scratched any dots off or anything. Blah, blah, blah. So we already know how to do number 1. Now here's what's interesting. You guys help me out. Here's something else my little brother, and I use him as a stand-in for everybody because a lot of people don't understand this. If I flip a coin, a normal coin hasn't been weighted, what's the probability that I get heads? 50%, right? What does that mean physically? What does that mean?
1 in 2 chance or 1 in 2 probability of landing on one side.
That's true, but I want you to really, I'm trying to open it up to something that I know is in the back of your heads. What the shit does that mean? If I flip a coin, this is my little brother's thinking. That doesn't mean a damn thing for a single flip. It will be a heads or it will be a tails. So what the hell's 50% got to do with anything? Well, probabilities only come into play when I do something a lot. So if I sat down and I flipped a coin 1,000 times, number one, I need to evaluate my life. But we're in the quarantine, so maybe now I'm like, who knows? That might be the most fun I have all day is flipping a coin 1,000 times. Number two, how many heads would you expect to show up if I flip a coin 1,000 times?
500.
500, right? Now, around 500, correct? Yeah. The only way I could know that is if I knew there was a 50% chance of getting heads. So probabilities only make sense in the long run. Does anyone play any poker? I'm not trying to get you to join a league with me or something. No, nobody plays any poker? Well, shoot. If you play poker and you play it right, you're going to lose a lot. but you're going to win a few times. And the winning a few times is big because then you make some good money. If there's a 20% chance of winning something when you do something, well, if you do that 100 times, how many times do you think you'll win? There's a 20% chance. Sorry, Kim.
20% or 20 times.
20 times. So if there is a 20% chance you'll win a tournament and you play 100 tournaments, you will win 20 times. And you can figure out what the average amount is that they pay out and go from there. So people that are in poker, and you can relate this to other things, they're okay with losing. They really are okay with losing because they know their method will eventually give them a win because of the probabilities. They know this, and normally get a pretty good amount of money. I have no idea if you're with me right now. So another example, rolling that die. If I rolled a die 6,000 times, how many fours would I expect to show up?
How many times?
6,000. You're like, what do you want from me? Well, go ahead, sir.
1,000 if you roll at
Yeah.
6.
1 out of 6 chance, so it'd be 1,000 out of 6,000. I would expect that many fours. Will I get exactly 1,000 fours? Probably not. Will it be close to 1,000 fours? Yes. I like it. Hey, Mikey. Okay, maybe. Okay, enough of that. I really get a lot out of one little thing. Let's see. Blah, blah, blah. Oh, yeah, so like this number 3, do that one for me real quick based on what we just did. Don't say anything out loud yet. If you roll a die 300 times, how many times would you expect it to land on 4? All right, who's got that answer? Let me get somebody else, Cameron. Who else has the answer?
50.
Yeah, because what do? You take 1/6 and then you multiply it by 300, right? Or you do 300 divided by 6. Same idea. Is everybody with me on that? No? If I multiply the probability of something happening times the number of times I do something, I'll get the number of times I expect that thing to happen. This is why, have you ever heard of like a 100-year flood? Anybody ever heard that expression? 100-year flood?
Yes.
So what the hell does that mean? That means that, can somebody figure out what that means? Like, what's the probability in a year that we'd have a flood so I'm thinking about like New Orleans or Louisiana, or somewhere along the water, right? Obviously, and we're along the water, but we'd have to have like a tidal wave or something, or global warming. But 100-year flood along the Mississippi. That would mean that 1 out of every 100 years, we'd get a flood like that. So it's a 1% chance of it happening. So when people hear that, or like California, let's talk about California since we live in California. The big one, what does that reference? We should know, living in California. The big one. Earthquake, yeah. So the chances that we'll get this huge earthquake are small, but then you multiply that by the number of years California's existed in this state, right? So people don't understand that things that have a very small chance of happening will still happen, right? Because if I have a very small chance over the course of my life of finding a 3-leaf clover or something. Or is it 4-leaf clover? Is it 4-leaf clover? Yeah, 4-leaf clover. It's still going to happen if I keep looking for them because I'm giving it a lot of chances to try to do it. So like it's very unlikely that I roll 18 sixes in a row in a die. But if I do it enough times, eventually I'm going to get 18 sixes in a row because it's out of a lot of times. Blah, 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 blah. Oh, wait, go back up. Oh, come on. That's easy. Let me see. I want to get to some nifty stuff. Yeah, so real quick on this one, if you flipped a penny 80 times, how many times would you expect it to land heads up?
40.
40. If I flipped a penny 80 times and I only got 2 heads, what am I justified to think? If you flip a coin, if you flip a penny 80 times and you only get 2 heads, what would you think about that penny?
It's fixed.
It's weighted.
Yeah, it's weighted, it's fixed, right? Is that like proof that it is? No. Is that really good evidence that it is? Yes. Why is it such good evidence it is? Because it was so far away from what we expected. Yes? So if any of you are going to take statistics, what I just said is interesting because what if I flipped 10 heads out of 80? That's still kind of weird, isn't it? What if I flipped 32 heads out of 80? Is that still kind of weird? So if you're going to take statistics, you're going to learn the math that will tell you exactly where unusual starts. Right? 2 is obviously unusual. 39 is obviously not unusual. What about 31 or something? Is that unusual? Well, I don't know. So it's this idea of how far away something is from what we expect. That is a huge thing you talk about in statistics. Okay, maybe. So that's in some people's future. I don't know how many of you guys are going to take statistics. Blah, 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 blah. All right, let's do yeah, here we go. Group work. Oh, this requires a little bit of work. Yeah, let me see. I might try to set that up for next time. Oh, yeah. So it's always better to have an actual experiment set up. So let me do this. Well, so the birthday thing is sort of an example of this. So if I said pick a number 1 through 20, we can see how many people pick the same number. But what's more interesting is what's the probability of that happening. So we sort of have to work our way up to that. How many, let me do this. Does anyone have a coin nearby? How many people can get a coin? Let me see if I can get a coin real quick. Do I have?
Run to my car real quick.
Okay, go get a coin, everybody. I'll do the same thing. All right, I got my lucky dime here. Oh wait, let's see. So everybody got a coin. Let's see. So this is going to require a little bit of honesty, all right? So everybody got a coin out there? Okay. Let me see. I think Carrie's still looking for a coin.
Yeah, I got
And then everybody else, that's a little black box with a name. I have no idea if you're even here. Okay. All right, I'm going to do this. So everybody flip the coin. Go ahead and flip it once. All right. All right. How many people got heads? Let me stop sharing here real quick. Oh, I'm sorry, Lauren. That's okay. Don't worry. Can you let me see. Yeah, can you either raise your hand in the participants, not on the picture. I'm not sure if you know how to do that. All right, this could be interesting. Could you yeah, there we go. Now we got some stuff happening. All right, so everybody that got a heads, raise your hand. Let me see. Looks like, is that everybody? One, two, okay. Well, a lot of people either are not here or did not get ahead. All right, so everybody that got ahead, flip your coin again. Everybody who didn't get ahead, you've lost. I'm sorry. Thanks for playing. So flip your coin again. See, I just lost. Damn. So flip the coin again. If you got ahead the first time, flip the coin again. All right. Anybody out there, Vu, are you telling me already? Anybody out there who just flipped the coin, get another head? Oh, you lost. Yeah, I lost too. So, all right, let's see you still in the running. Okay, all right. Now, so I've only got 3 people in the running still, it looks like. Those of you who got another head last time, flip the coin again. All right. Now, did you get another head? Damn. All right, so we got 2 people, 3 people in the running still. Okay, so everybody got a head, flip the coin again. Okay, Ruben's in there too. So if you got another head last time, flip it again. Let me clear everybody. Ruben's out. Linnell's still in. Anybody else get another head? Linnell, so Linnell's got 4. Linnell, flip it again. Don't worry, I'm not gonna, this is the last time I'm gonna go. Oh, holy shit. All right. So real quick, let me see if you guys get this idea. And this might be the last idea to talk about. So Linnell just got 5 heads in a row. What's the probability of that happening? So let's figure this out. Let's figure this out together. What was the probability that he got a head on the first flip?
50%.
50%. Right? In fact, everybody had a 50% chance of getting ahead on the first flip. I have a feeling that some of us are not really here or did not participate because I had so few people. I would expect around half of us to have gotten ahead. It's not impossible to get as few as we did, but I think it's more likely that some of us weren't participating. Some of us might not have any coins. I understand. So 50% of the people should have gotten ahead on the first flip. That's what I expect. What percentage of those people would then get another head on the second flip?
50%.
50%. So what have we got so far? 50% of 50%. So half of half. And of course, what's half of half?
25.
Yes, 25%, 1/4. And then I just keep going. So 5 times in a row. If you do 0.5 times 0.5 times, or just 0.5 to the 5th power, because it's 50% of 50% of 50%. Do you guys see what I'm saying? So if you do 0.5 to the 5th power, what do you get?
3.12%.
Yes. Let me do one little thing here. All right, now let me push this one. Let me push this a little bit. This is a little further than we have to go. I don't know how many people are still with me, but this is how, do you remember how you do repeated discounts? Don't you raise that discount you're doing to, or markups? So this is really working the exact same ways. It's half of half of half of half. So I expected fewer and fewer hands to go up each time, because it's half of this and then half of those and then half of those remaining and then half of those remaining is what I expect to happen. So we got 0.03125, right, on the calculator. If you multiply that by 29 people, remember what we did. If I flip a coin, if I roll a die 300 times, I expect 54s, right? That we did that earlier. You with me? We did the probability of a 4 times the number of flips. So if I multiply the probability we just got by 29 people, because there's 29 people in here, assuming everybody participated, I get 0.9. What the shit does that mean, Jeff? That means I expect about 0.9 people, or let's round it to one person, that would end up getting 5 heads. That's kind of cool that that happened. Did it have to happen exactly that way? No, that's the thing about probability. But I expect it to happen close to that, and we just happen to get almost exactly what I expected. All right, maybe, I don't know if any of that got through. Probabilities get weird. That's one thing to get used to. Probabilities get weird, and that's why we have to trust the math that we build to work with them, because they're not things that we can just go, does that make sense? I really don't have a freaking clue if it makes sense, because it's not something hardwired in us. We have to understand the mathematics to really get to the answer. All right. Okay. Maybe. All right. So I'm gonna cut it short again today. Why not? We're gonna stop here at 10. I kind of wanted to have shorter classes anyway. I don't want to keep everybody on Zoom too long. If you have any questions, we're obviously got more stuff to do in 1-6. Today we talked a lot about ideas. We're going to do some more specifics tomorrow. Okay. But if anybody has any questions or anything, just you can hang out. Otherwise, class is over for today. So let me know if you have any questions.
I do have a question.
Yes.
I was doing the homework on 1-5 and I was on the last problem of applications, and it shows the graphs, the scatter plot for the two.
Yeah.
For question 8 on 1-4, and my question is that if I'm gonna set up this, you know, what do you call it, like miles and taxi fare on the other one, it was 1,000 and
I got them. I'm sorry. Let me see. Let me look it up real quick. 1-4. It's talking about 1-4 data, right?
Mm-hmm.
So numbers 7 and 8. Okay, taxi fare. Okay, I'm with you.
And then
So
what
like
was
the start would be 0, right? Okay.
Okay. So my question is the taxi fare is like, I think it was between $1 and $4 or $5 or something. And then the other one, and I have to look it back up. Let me go in the back. I can't remember off the top of my head. It was, between 12,000 and 19,000, and it was years. So how would I put the two?
No, there's 2 different graphs.
Perfect.
So, right, I give you 2 different graphs. Yeah. Because otherwise, I'd agree with you. You can't put both of those data on the same graph.
Okay, that's.
Yeah.
Okay, I just wanted to make sure that is what I was supposed to do. Okay, and that answers my question. Thank you.
Same thing, Jeff. I didn't quite. I was trying to get to the pay because I kind of stopped right there. Can you hear me?
Yes.
So we're going back on that particular one to 1-4. It's telling us to go back to page 7 and 8.
Question 7 and 8.
Question 7 and 8, yeah.
So let me see.
So I'm basing these 2 graphs that I'm going to make off of question 7 and 8.
That's right. So here's the data from 7 and 8 here, right? So on the x-axis,
Okay.
these would go on the x-axis: 0, 1, 2, 3, 4, 5. And the y-axis, you just have to pick a good scale so that all of these show up, right? So your y-axis scale has to be able to go up and show up to 1530, right?
Up to 1530 in the other one here up to
The x-axis
19.5.
This one has the same x-axis, right? 0, 1, 2, 3, 4, 5. But then its y-axis, you're going to have, you can start at 12,000 and go up to get up to like 20,000 so that this last guy can fit.
Right.
And that's sort of like using the thing that Nikisha suggested last time, which is don't start at 0, right? You can start at like 10,000 and maybe go up by 10,000, 12,000, 14,000, 16,000, right? So then you get up to 20,000.
Right.
So, yeah, there you go. That's
Okay.
so it is another problem about figuring out a good scale to show the data points.
All righty. All right. Thanks a lot.
Everybody else okay out there?
I wanted to see if you could also show me how to do those right there on the screen.
Oh, these problems specifically, not 1-5, but this right here, what you got to do here?
Yes, I
Okay.
was so stuck I did not know, and I just want someone to be able to explain to me like how the process is done.
So can you tell me linear growth is based on doing what over and over and over? Versus
Hold on, let me go to the page.
I think it's added the same amount per year.
yes.
Per
So linear growth is adding the same amount each step,
each step, yeah.
right? And then, are you with me, Giovanna?
Yes.
So linear growth is if they add the same amount each year. Exponential growth, and this is kind of easy to remember because what are exponents based on? What operation are exponents based on? Like if I said do 7 squared, what would you do with 7?
Double it.
Yes.
Not double it, that'd be 14. What do you mean?
Yeah.
Multiplication. So exponential growth is if they keep multiplying by the same amount. So how do you look at number 7 to see which one it might be? If you take 5, go ahead.
Do you figure out the difference from the first one to the second?
So if you see the differences between one and the one before it, and that difference is the same, that means they added that amount every time. So to check if it's linear, you subtract, since that'll show you if they kept adding the same thing. So what do you do to check if it's exponential?
See if it doubled.
Well, see, not
see if you multiply times 2.
no, that's too specific. If linear is addition, so you subtract things to see if they added the same thing. Exponential is multiplication, so therefore you're going to divide. So in number 8, if you divide 13,200 by 12,000, you'll get something. Then if you divide 14,520 by 13,200, is that the same thing? That'll show you, did they keep multiplying by the same number to get the next? Does that make sense? So if you have a calculator right there, can you divide 13,200 by 12,000?
1.1.
Yeah. You see that, Giovanna?
Yes, but okay. So you divide the 12 by what number? By the
You
5
divide,
years?
you divide one data point by the one before it. So you divide
Okay.
13,200 by 12,000. Because it's
Okay.
obviously not linear. Is that okay for me to say? Do you keep adding the same thing at number 8? No, because from 12 to 13, you add 1,200, and then you add 1,300 something. So it's obviously not linear. So I would check to see if it's linear first by seeing if they added the same thing, and they didn't. Then I see if they multiplied the same thing. Go ahead.
I see 1.1 for 12 to 13 and 1.1 from 14 to 13. So
yeah, there you go. So it looks like in number 8, they keep multiplying by 1.1. So that's 1.10, which we know is a 10% increase. So number 8 looks to be exponential growth because it looks like they keep multiplying by 1.1.
And that's what we have to do is write the exponential growth or not?
Yes. And then
So
they ask
it's not doing work?
No, look here. It also says find the next value.
Oh, okay.
So then you just do the same thing to 19,000. You just multiply by 1.1 again.
So at this point, the numbers on the side, like 1, 2, year 3, and 4 don't matter.
The only thing that matters is that they keep representing the same step. One step, one step, one step. Do you see what I'm saying?
Yes, it makes sense. Okay, I understand now.
Otherwise, it wouldn't be fair to compare these unless they were one step apart here. Yeah. That's the only thing that matters about that first row is that it's consistent. 0, 1, 2, 3. Yeah.
Okay.
Otherwise, the numbers don't matter.
I got that. Now it makes sense. Now I have another question if you don't mind.
No.
Okay. On the 1.4 first page, the page 55 with 1, 2, 3, and 4, it said that the pizza would increase 5% next year. And so the number on the thing, on the items on the graph item, small potatoes, and you have to figure out the 5% on each of them. So I just want to make sure I did it right because I usually do this with rental agreements. I increase the rent by 3%. And so I use that, but I kept putting the 12 because it increases like every month since they pay rent monthly, and I kept putting the 12, and I kept thinking, why am I putting 12 if it's not each month that it's increased, it's only increasing by once. So
somebody else did that same thing. I wonder if they have sort of a similar job to you, but go ahead. Sorry.
And so I got that it increased by 28 cents, and that's why it went from 560 to 588. So I just want to make sure that is because I did 0.05 times the 5.60, and I got 0.28, which would be the 28 cents increase. Then I added it again by the
And so the shortcut to that is to just multiply 5.60 times 1.05. That's the shortcut.
but why 1.05?
So you ready? Okay.
Yeah.
I'm going to stop sharing so I can do this up on the board.
Okay.
I really want this to make sense because the shortcut kicks so much ass, and maybe you can actually use it in your work. So what you just described to me is you took 560 and you added it to 560 times 0.05, right?
Yeah, I did the
Yeah, I'm with you.
0.05 first.
And that is, yeah, I'm with you. But that's basically, you figured that out and added that to there. Okay.
Yeah.
Let me raise this up. So if I take a 560 out of this, which sounds weird, but it leads to a shortcut. Because if I needed to do 80 of these, this method would so suck. But if I realize 560 divided by 560 is 1, take a 560 out, I'm left with 0.05. So all I just did was I did distribution backwards, right?
Yeah.
So
Okay.
5.60 times 1.05. So now if I wanted to do 2 increases, I would just put a 2 there. If I wanted to do 20, I would put a 20 there. And I can get the end result immediately instead of having to do it step by step.
Oh, I see. For like when it increases in 2 years and increases in 3 years, is that what when you do it?
Yes. So yeah. So later when they say the pizza increases 1, 2, 3, and then they go 10, there's how you can do 10 real quick. Do 10 of these to this. That's what that means. So 10 5% increases on top of this. You'll get the answer without having to do this and then add it and then this again and then add it. Oh my God.
Yeah, I saw that on the number 3 one, and it made sense then.
Yes.
But I didn't get it until I finished the whole problem. That 3 was the last one I figured out.
The little table on number 2, I think it is, right, with the milk and whatever.
Yeah.
It's 1 increase. So you actually can do it this way and it's not a big deal, but this is the slight shortcut is with the first power here. So you just take the amount times 1.05. Bam.
Okay, I see. Makes sense. No, that makes sense.
I like it.
All right. Thank you so much. I appreciate that.
You're welcome. All right. How's everybody else out there?
I have a question about one of the problems on the quiz. Number 3, when the numerator is greater than the denominator, do you still do the same thing, like try to find what goes into, you know how I don't know how to explain it. You know,
I-
Are you looking at number 1 or
number 2D.
2D? Okay, let me look up yours real quick. See what you did. All right, so 2D. Oh, okay. So the only mistake you made, do you see how you did the 5 and the 15?
Mm-hmm.
Beautiful. Keep going. Do the 14 and the 21. What number goes into both of those?
7, so I put 7 times 3, and then at the 14, I put 7 times 2.
Yep. So the 7s die. So then you get 3 over 1.
3 over 2.
Because your result isn't wrong. It's just not reduced. But if you reduce when they're small numbers, that's easier than reducing when they get big. So that's why I was trying to circle that 21 and 14 so you can see I can reduce then. It's easier to see that.
So I just left it, and then I put the 63 and 14. I divided. It got 4.5, and I was like, I don't know if that's it, but I did put the 7 times 3 and the 7 times 2. So you just cross out the 7s, and whatever is left is what the fraction will become.
That's right. You just multiply across whoever the survivors are. Yeah.
Okay, perfect. Okay.
And that's just reducing it before you multiply and make it big. You reduce it while they're small. That makes it easy. Yeah.
Okay.
Cool.
Okay. Thank you.
You're welcome. How's everybody else? All right. I'm going to head out. Oh. All right. I'm going to head out.